Okay, so today we're going to be talking about least squares regression lines and what you can do with those and what information that can tell you. So the first thing we're going to start off is what the regression line is in general. So the regression line is just going to be the line that will help you, it can help you predict a value of y if you have a given value of x. Basically, the line is showing you how the response variable changes as the explanatory variable changes. So let's look at this example and kind of use this in context and see what this means. You've worked with these before in math class, and you're going to see it's going to be the same. Once again, you're going to have some slightly different terminology and such. Okay, so let's look at this example real quick because this example will kind of carry us through a lot. So everyone knows that cars and trucks lose value the more they are driven. Can we predict the price of a used Ford F-150 Super Crew 4x4 if we know how many miles it has on the odometer? A random sample of 16 used Ford F-150 Super Crew 4x4s was selected from among those listed for sale at autotrader.com. The number of miles driven and price in dollars were recorded for each of the trucks. Here are the data. So we've got our miles driven and we've got our prices there for our trucks. Figure 3.7 is a scatter plot of the data. So we've got our scatter plot over here. The plot shows a moderately strong negative linear association between miles driven and price with no outliers. The correlation is R equals negative 0.815. So we've got a negative association here. It's relatively strong. The line on the plot is a regression line for predicting price from miles driven. So what we have here is most of y'all have heard termed it basically your line of best fit. So what we have in our scatter plot down here is you can see your regression line, okay? And you can use that regression line to predict the change in the price, so the change in Y, based on the change in the miles that are driven. The regression line is a model for our data. So our normal density curves, those were also models for our data. So sometimes on test questions, you guys will see where it will say what would be the appropriate model for the data. That's what they mean. Things like density curves and regression lines, those count as models of the data. They're showing the trends and what the data looks like. So let's look at some vocabulary here associated with our regression line. So this is the formula that we use for our regression line. I know you guys are used to y equals, mx plus b? Yeah, y equals mx plus b. Okay, so we have them in a slightly different order. B is still our slope. Whatever's in front of x is always going to be your slope. Okay, so b is still our slope. Y hat, so this kind of odd looking y here, that is read as y hat. That's our predicted value of the value of y for a given value of the explanatory variable x. So y hat is our prediction using this regression line. Okay, and then a is the y-intercept. Okay, that's our predicted value of y when x is equal to 0. Okay, so it looks a little bit different than what you're used to with slope of a line equation. Okay, but the stuff in it is still the same. So y hat is our predicted value, and you have to write it like that every time. It is the letter y with literally a little pointy hat over it. And when you write your context, you'll write your context, like for instance, our context in this case is price. So what that stands for, what that means is this is our predicted price. That's what the little hat stands for. If you don't have the hat and you put just a Y, that means that that is the actual price, which it may not be. It's the actual value, in this case the actual price, which it may not be. So you have to make sure you use that notation correctly. So on your formula sheet, you are going to have this equation, but it's going to look different. Okay, on your formula sheet, you're going to have your y hat equals b naught plus b1 x. So either one is acceptable. Both this one and this one are both acceptable. This is the one that you see on your formula chart, the b naught plus b1. However, this is the one your book chooses to use because that's how your calculator displays it. That's what your calculator chooses to use, and the formula just looks a little bit more forward, a little bit more straightforward. So if you're showing your work, you are totally welcome to use this formula to show your work. Okay? If you don't remember this formula though, this is again on your formula chart. You just need to realize that regardless of the letter, whether it's M, whether it's B1, whether it's B, whatever is the coefficient for the X is the slope, no matter what. Okay, so let's look at what is expected of you when you're asked to put this into context, when you're asked to interpret. Remember, your interpretation is explaining what it means in context. For example, when you interpret percentile, you say, this is 73% of the teams, won less games than they did. And when you interpret z-score, or you tell me how many standard deviations above or below the mean it is. So with slope and y-intercept, you may also be asked to interpret those. So for this particular problem, you're asked to identify the slope and y-intercept and then interpret each value in context. So our slope, is negative 0.1629. Okay, and so what that tells us is that it's negative, so it's going down. So it's telling us that the Y, the price of the used Ford, so the price of the used Ford is predicted, because that's what we're doing, because we're using, this is our Y hat, right? So it is predicted to go down or to decrease by 0.1629 for each additional mile that the truck has been driven. So when you interpret slope, what I've seen a lot is that when people interpret slope, we interpret it backwards. Okay? That we say, like we would say something like the miles driven would decrease the cost. Okay? So when you interpret slope, you're taking this number is your value of how much y is going to change. Okay? It's going to be your value of how much y will change for every one value of x. So it's how much y will change for every one value of x. You'll notice in our interpretation of context here, okay, we've got the price of the used Ford, so that's my y, that's my context. The price of the used Ford is predicted to go down, because it's negative, by 0.1629, so that's my change in y. That's how much money I think the price will go down for each additional, not even right mile. So there's my 1 unit right there, mile, for every 1 unit x. So every additional mile the truck has been driven, because the truck has probably been driven, these trucks aren't like this one was driven 20,001 miles and this one was driven 20,002 miles. If you look at your scale for miles here, you're going from 0 to 160,000 miles. Okay, so that's how you're going to interpret slope. So if we want to kind of sentence stem this out, that would look like, right, what you're going to kind of start with every time, okay, is your description of y. So your context or your description for y, okay, is predicted to, and then you're going to go up or down. So you'd have to choose those. So your description for y, so your context, put y in context, is predicted to go up or down by, and then you put your actual slope value in here. So 0.169, okay, for every one additional x. And so x would need to be in context. Okay, so that's kind of your sentence stem for describing slope. You describe y in context. You say is predicted to. You choose to go up or down by whatever the value of the slope is for every one additional x in context. Okay, we're gonna work a lot. We do a lot in the second semester, and we're gonna practice it more in the first semester now. Working basically on sentence stems that we just say the same thing over and over and over again, so we won't mess it up. Okay, as most of you guys are aware, and you know how to do this, you can predict using your regression line. So basically, by putting your line of best fit in there, I can predict the price. I can get my y hat. So our problem here, if the used Ford F-150 has 100,000 miles driven, so we're going to predict the price. Okay, so we can just plug that into our equation. All right, we have our price equals 38,257 minus, that's my y-intercept, right? That is when it has been driven 0 miles. Okay, and then times, and it's gone 100,000 miles. So I can predict my price from there, okay, which would be $21,967. I could predict that off of the graph as well. Using my regression line, I could follow that over, okay, to where that hits on the y-axis. What I cannot do is extrapolate. I cannot try to predict values that are way outside of the data that was given to us. Like, for instance, we have, I think our truck here with the biggest miles is about 140,000, maybe a little bit more. I couldn't try to predict the price of a truck that had 500,000 miles on it. Okay, so I cannot extrapolate. We are not making predictions using X values that are way outside of the data that we have. Okay, so let's look at another example with these. So some data were collected on the weight of a male white laboratory rat for the first 25 weeks after its birth. A scatter plot of the weight in grams and time since birth in weeks shows a fairly strong positive linear relationship. Okay, so let's kind of review real quick what that would mean. Fairly strong positive linear relationship. So basically, sorry when I do that. Okay, so basically we've got a graph that is going, it's going in this direction, right? And it's fairly strong, so the dots are pretty close together, right? If I drew my oval around my data points, it would be pretty narrow, right? My linear regression equation is my predicted weight, so my y hat equals 100, so that's my y-intercept, right, plus 40, which is my slope, times time. Models the data fairly well. Remember, this is a model of our data. So what is the slope of the regression line? Explain what it means in context. So our slope here is 40. So in context, what does that mean? Okay, well, let's kind of go with our sentence stem here. Okay, so our sentence stem was putting our y in context. So the weight of the rat is predicted, and we have to positive or negative it here. Okay, so increase or decrease, well, it's a positive slope, so predicted to increase by whatever the slope value is, 40, okay, and we're measuring it in grams, so by 40 grams, and then put my x in context for the first 25 weeks, so for each additional week. Use my sentence stem, right? So the weight of the rat, my y in context, is predicted to go up by 40 grams for each additional week that passes, however you want to, however you want to word that exactly. Okay, so number 2, what is the y-intercept? So our y-intercept here in this equation is going to be, where's my equation? Our y-intercept here is going to be 100. What that means in context, okay, well, our y-intercept, right, our y-intercept is when x equals 0, right? Here's my x, here's my y. So when x equals 0, y equals 100. Let's go ahead and put that here. All right, and we've got this strong positive linear relationship here. So what that means is at 0 time, right, because this is weeks, the rat weighs 100 grams. Well, when it's born, right? So that would be 0 time. A newborn rat has a predicted weight because remember this is predicted of 100 grams. Number 3, predict the rat's weight after 16 weeks and show your work. Okay, so showing your work for this would count just to sub it into the equation, right? So y hat equals 100 plus 40 times 16 equals 740 grams. That would be my predicted weight of the rat after 16 weeks. Number 4 asks, should you use this line to predict the rat's weight at age 2 years? Use the equation to make the prediction and think about the reasonableness of the result. Okay, so if we use the equation to make the prediction, over the course of 2 years, there are 104 weeks, because my time here is in weeks. So to make the prediction, I'm going to have y hat equals 100 plus 40 times 104, which equals 4,260 grams. They told you there that there are 450 grams in a pound, so that you could convert that if you needed to. Okay, in pounds, that would be almost 9.5 pounds. Okay, that's a ridiculously giant, crazy, humongous rat. Okay, this would be an example of extrapolation. We can't we went out 25 weeks. We can't go out 104 weeks from there. Okay, so it would be an unreasonable thing due to our extrapolation. So let's look at what residuals are then. Residuals are basically our difference between the observed value, so the actual value, and the predicted value that's made by the regression line. For instance, this is our truck data again on this graph here. Okay, we've got our regression line in there, and all these little lines right here going up off the graph and going down below it, those are our residuals. There's our data point there, okay, and then the residual is that distance, basically it is away from the line, because the line would give us our predicted value, and that's our actual value. So our formula for calculating a residual is just our observed y, so the actual y minus the predicted y. You've seen this a lot before, whether you realized it or not. In z-scores, we did our observed value, our data point, minus our expected mean, our predicted mean. To calculate standard deviation, again, we do our data point minus our predicted or expected mean. And so for residuals, we're doing our observed or actual value minus our predicted value. Okay, so actual minus predicted, so that can help you with the order, right? The order is AP. Okay, actual minus predicted. So let's look at a quick example of this. So back to the trucks again. Find and interpret the residual for the Ford F-150 that had 70,583 miles driven and a price of $21,994. So this is our regression line information right here. Okay, the actual price was $21,994. I calculated my predicted price there. Remember, my order here is actual minus predicted, or AP. So I take my actual price, I subtract from the predicted price, and I get a negative $4,765. So now I found a value, I calculated my value, but I need to interpret that and put that in context because this was a two-part thing. It asked you to find it and interpret it. So what this means is we need to address that positive and negative sign, right? So the actual price of this truck is $4,765 lower than expected based on its mileage. The actual price might be lower than predicted as a result of other factors. For example, the truck may have been in an accident or may need a new paint job. You don't necessarily need to take it that far, right? You have to definitely do this first sentence. The actual price of the truck is $4,765 lower than expected based on the mileage, all the context, right? Based on your X, based on your mileage. As to why it's lower, that's iffy as to whether you really need to do that every time or not. We're going to generate, we've kind of already given you the sentence stem for slope, but we're going to generate in class some sentence stems for context of y-intercept, context of residual, and just kind of keep a running list of sentence stems so that you just plug your context in for your different problems. Okay, so we will be using a lot what we call the least squares regression line. And the least squares regression line is basically it's our line that's going to make the sum of the squared residuals as small as possible. We have to use the squared residuals just like we had to calculate variance for standard deviation. We had to square everything because otherwise all your residuals will add up to 0 because you'll have, again, remember you're trying to get this line to go, sorry, I keep doing that tonight. You're trying to get this line to go where you're going to have even distribution around the line. So you're going to have your positive and negative residuals should start to cancel each other out. So your least squares regression line is of y on x is the line that makes the sum of the squared residuals as small as possible. Okay, you can see this here in graphic form, your squared residuals. Okay, and so you're trying to make the sum of those as small as possible. Okay, so hopefully you have your calculators with you, and we can look at how to do this on the calculator real quick. Okay, we'll also practice this in class too. So using your F-150 Ford truck data, go ahead and put the miles driven in L1 and the price data in L2. Okay, you can go ahead and make your scatter plot. Remember, that's the one all the way over to the right on your plots. So pause it until you've put all that data in. Okay, and so now to actually draw your line. So to actually draw your line, that's going to be this chunk down here on the bottom. Okay, so press Stat, choose Calc, and then you'll see the Lin Reg. And remember how we said your calculator uses the A plus BX. Okay, this is what they're referring to. Okay, so you're going to, this is all going to pop up. Okay, and so you're going to put in all of your So after you put in all of your information here, so your X list should, in this example, should have been L1, your Y list should be L2. Make sure you type those in every time. Your calculator will default to L1 and L2, but if you type those in L3 and L4 or L2 and L5, okay, you're going to get weird stuff. You leave the frequency list blank. Store reg equation, so store the regression equation under Y1 and then choose calculate. And you'll get all of this information here. Okay, you'll get your slope, you've got your y-intercept, you've got your r value, you've got your correlation there. Okay, and then you can go ahead and graph it. Okay, and so when you graph it, go to your y equals screen, right? So to graph it, go to your y equals screen because you should have saved this under y1. Make sure all the other y equals are turned off. Okay, and then go ahead and graph that equation, and you can use your zoom stat button to see it better, and you'll get that line. Okay, so let's look at what we call a residual plot. A residual plot is going to be one of those things that's going to help us determine if a linear model is appropriate. Remember, we had normal probability plots before to help us determine if the data was approximately normal. We looked for a linear pattern. Okay, so a residual plot is a scatter plot of the residuals against the explanatory variable. So what they mean by that, you can see the example down here and in graph B on the right here. So my x stays the same. That's what we mean by against the explanatory variable. and my residuals come over here on the y. And for a graph like this, the mean is always 0. The mean of the residuals is going to be 0. So let's look at what we've got going on up here. So we've got the F-150 data again, okay, and we've got one truck that had 68,474 miles driven and a price of 33,961. Okay, we know that it's higher because this one is above the line. Okay, and we go ahead and calculate our residual, our actual minus predicted, and we get a 6,858. So this truck cost almost $7,000 more than expected based on the mileage. So $6,858 more than expected based on the mileage. So you can go through and you can calculate all of the residuals for this data set. And when we go and we graph all of those residuals, okay, we get our residual plot. And this particular residual plot that we have over here on the right, you'll notice doesn't have any sort of pattern. Okay, that's actually what you're looking for with a residual plot to determine if a linear model is appropriate. If your residual plot looks like this, kind of scattered approximately half below, half above, looking just kind of scattered throughout, because remember our mean is going to be 0, okay, then a linear model will work for this data set. It's good for this data set. And we can make residual plots on our calculator, and we'll look at that in class, how to do that in class. I think that's easier when we're in person than trying to do it this way. I want to take a second and look at a couple of quick examples here of when a linear model would not be a good model for the data. So both of these are residual plots, and you'll notice that I don't have that scatter pattern, about half of them above, half of them below. I have these curves, okay, and so these curves here, and here of my residuals do not indicate that a linear model would be good for this data. So again, you want to see that scattering above and below to be able to use a linear model. So let's do one last example and then we'll be done for tonight. Okay, so look at what we've got going on here. So this is a residual plot for the least squares regression of pack weight on hikers, so the backpack weight on the body weight for 8 hikers. So here's my residuals plotted on my X, so my body weight. So basically I'm trying to use body weight to predict the weight of the backpack that the hiker can or would be carrying. So the first question, one of the hikers had a residual of nearly 4 pounds. Interpret this value. Well, it's a positive value, so we know that it's heavier or it's above what was expected. So the backpack, using my Y context here, the backpack for this hiker was almost 4 pounds heavier than expected based on the weight of the hiker. So based on my X. Again, we're going to be trying to put together sentence stems for all of these things in class. Number 2, based on the residual plot, is a linear model appropriate for this data? Okay, so what do we see going on here? Okay, there seems to be some scattering, but it's a pattern of scattering. It's like a up, down, up, kind of down, but it's a pattern. It's not super random. So a linear model would actually not be appropriate for this data. Okay, we'll look at more of this stuff in class and work with our calculators and stuff then.